We're continuing Skill 1, Section 2.6, from where we left off. And if you recall, we just did some problems that involved us finding limits of expressions as we were approaching infinity or negative infinity. So in all 3 or 4 of those examples, we ended up approaching a number. Whether it was a positive or not negative, it was a finite value. Well, what happens if, as you move to the right, the function becomes unbounded? We need to have some notation that will illustrate that to us. So if we look here, this tells us that the y coordinates are getting infinitely large as x gets larger and larger on the right-hand side. So graphically, this statement will tell us that we have a picture that is growing as we move to the right. If I were to change this to a negative, then this would say my y values are becoming more and more negative as x moves to the right. So that would correspond to a picture that was doing something like this. If I change this infinity to a negative and keep both of them, then here my y coordinates are becoming smaller and smaller in the negative direction as I move left. So that would correspond to a graph that's doing this. And my last incarnation would be if I change those outputs to positive. As I'm moving left, my y coordinates are becoming unbounded. So you need to be able to interpret these types of statements visually into graphical representations of the same information. So we can now apply that analytically. If we think about this behavior of the exponential 3 to the x, we know since the base is larger than 1 that this graph is going to be growing on the right and flat on the left. And if we look at what this limit is asking us to determine, it wants to know what are happening to the y coordinates on this exponential function as x moves further and further to the right. Well, as we can see, we are getting bigger and bigger, so our limit would be written as infinity. Now on this one, we're on the exact same graph, only now we're traveling to the left. So if I hop on this curve and move to the left, we can see that the y coordinates are getting closer and closer to 0. Now if we move to part C, here we have an exponential that is growing on the right, and we are comparing it to a polynomial whose dominant term is the 4x to the 8th. Now in this particular case, we cannot do just our dominant terms and get a nice reduced answer out. That's because one of the terms, the e to the x, is growing significantly faster than the polynomial. So as x becomes infinitely large, this e to the x in comparison to the 4x to the 8th will be much, much larger. So we have a gigantic number divided by a relatively small number in comparison. That means we are blowing up to positive infinity. The final example, part D, is a little trickier because at first instinct you might want to select the dominant term, which is the square root of x squared, which as you're traveling to the left will be the same as the opposite of x, and then you add x, so you might think that you end up with 0 as your answer. Well, if we want to verify that using our calculators, we will soon discover that it doesn't work that way. So let's go to our home, our y equals, edit the one we had in there before. We'll do an x squared plus an x plus a 1, and then add an x. And we want to look on the left side. So if I look on the left side, that means I will do a zoom 6 just to start off with. And we'll look to see what's happening, and we appear to not be focused. So let me auto this. We can see here that if I look on the left, I'm not quite matching up with that x-axis, and if my limit's supposed to be 0, it's not really working. So maybe it's just that we haven't looked far enough on the left-hand side. So I'm going to change the window using Diamond F2, and I'm going to go all the way out to -1,000,000. Let's see if that gets any better. I'll graph it again. And notice that the graph is still tracking below the x-axis. So even though I went out to -1,000,000, I'm not getting any closer to that supposed limit of 0 that I thought I should have. If I trace just to verify, we can see that that y-coordinate is getting closer and closer to a negative 1/2. So based on our graph, we should be able to come up with, analytically, a way for this to equal negative 1/2. So let's look at what is going on. If I look here, the reason I was able to compare growth rates is because I had a fraction. So what we want to do is we want to create a fraction so that we can then determine dominant terms. To create that fraction in a way that will help us, I'm going to multiply by the conjugate of the top on both the top and bottom. So I'm making a smart choice for 1 to alter the way this fraction looks without changing its value. When I do that on the top and multiply it out, I will get an x squared plus an x plus a 1 minus an x squared. And on the bottom, I will keep that conjugate as is. Now notice on the top that the x squareds cancel. So now on top, my dominant term is going to be x. And on the bottom, my dominant terms will be this x squared in the square root and this other negative x. Notice both of these essentially have the same power, so they're equally powerful as we move to the left. If I simplify that square root on the bottom like we did on the previous 2 slides ago, I guess, then we are comparing this limit where we've got an x on top and a negative x minus an x on the bottom. If I simplify that now, we can see that x over a negative 2x, and here comes that negative 1/2 that we saw graphically.